Hello everyone, welcome back to the channel. Today we are going to learn one of the most powerful analytical technique in modern chemistry, GCMS method development. Whether you're working in pharmaceutical, environmental testing, food safety or forensic, mastering this technique is absolutely essential. By the end of this video, you'll understand the complete workflow for developing and validating a robust GCMS method with a special focus on the critical MS-MS optimization strategies that separate good methods from great ones. We'll cover everything from initial planning to advanced collision energy optimization techniques. So let's get started. So what is GCMS? First, let's quickly review what GCMS actually is. GC stands for gas chromatography, which separates volatile compound based on their interaction with the stationary phase inside a column. The MS or Tandem mass spectrometry provides two stages of mass analysis in a triple quadrupole configuration, giving us incredible selectivity and sensitivity. The workflow goes like this: sample injection into GC. Compounds separate as they travel through the column. They enter the first quadrupole which selects specific ions. Selected ions are fragmented in the collision cell. Fragment ions are analyzed in the third quadrupole. So this tandem approach is what makes GCMS so powerful. We are not just measuring molecular weight, we are confirming identity through specific fragmentation patterns. This dramatically reduces false positives and allows detection at parts per trillion levels in complex matrices. Before you touch any instrument, successful method development start with through planning. Ask yourself these critical questions. What are my analytical objectives? Are you doing screening or quantitation? What's your required sensitivity? What metrics are you going to analyze? Research existing methods. Define your validation parameters upfront. Now let's talk about your optimizing your gas chromatography separation. Now column selection in this is very crucial. Your stationary phase determines separation. So the first type of columns is non-polar column that contains about 5% of your phenyl and 95% of your dimethyl polysiloxane. Example of these columns are DB5MS, HB5MS, RXI5MS. It consists of wide polarity range. Then comes your polar column. Examples are polyethylene glycol and wax phases. And it contains about it can go up to temperature typically 260 degrees Celsius, and it is excellent for analysis of alcohol, acids, carbonyl compounds. Then coming to your mid polarity columns, it consists of 50% phenyl phases for aromatic compounds. Then coming to ultra low bleed MS columns. These columns are essential because column bleed can create background noise that reduces sensitivity and can interfere with your mass spectral library matching. Let's talk about temperature programming. This is where art meets science. Your temperature program controls your retention time, peak shape, resolution, and analysis time. So the key parameters to optimize is you need to start with the initial temperature, that is, start below the boiling point of your earliest eluting compound. So the common range is 40 to 80 degrees Celsius, and you have to keep hold time about 0.5 to 5 minutes for peak focusing. Then coming to ramping rates. Slow ramp about 2 to 10 degrees Celsius per minute. It is for better resolution, but it causes longer runtime. And fast ramps you can go about 20 to 40 degrees Celsius per minute. This will give you shorter analysis time but potential co-elution. Multiple ramps for complex mixture optimize separation where needed. Then coming to final temperature, it should exceed the boiling point of your highest boiling point of analyte. Typically it ranges from 250 to 320 degrees Celsius depending on your column. So the whole time it ensures complete elution and bakeout. Typically, you have to keep it for 2 to 10 minutes. Now let's talk about your carrier gas. Helium will give you best chromatographic performances, but it is expensive. Hydrogen, it will give you faster analysis with improved efficiency, but safety considerations requires proper venting of hydrogen gas. Third one is nitrogen. It is most economical but requires method re-optimization. Now the flow rate of your column flow could be about 1 to 1.5 ml per minute for 0.25 mm ID columns. Talking about your injection parameters, the temperature would usually be between 250 to 280 degrees Celsius. It must instantly vaporize all your analytes. Let's talk about split versus splitless mode. So if your sample is concentrated, then you need to go with split mode. Therefore, it would give you better peak shape and it would prevent any overloading in your column. And if you're analyzing trace analyte, then you need to go with splitless mode. It will give you better sensitivity and all sample will reach your column. Injection volume would be typically 1 ml. Now let's learn about MS-MS optimization. So before coming to optimization, let's understand what is triple quadrupole system. So triple quadrupole system consists of Q1, Q2 and Q3, where Q1 and Q3 are your mass analyzers, where your mass is getting filtered, and Q2 is nothing but your collision cell, where fragmentation happens of your precursor ion. So in Q1, it filters your masses, whatever you have selected your precursor ion, and that precursor ion will enter Q2 and will be fragmented. So the fragments then go to Q3 and whichever product ions you have selected for detection, that will be filtered. Before we even get to the quadrupoles, your ion source optimization is critical. So let's talk about your electron ionization parameters. Electron energy, the standard electron volt is 70 because it provides reproducible fragmentation. Therefore, GCMS has NIST libraries. Then emission current, it typically ranges from 35 to 50 microamperes. It affects your ion abundance. Then comes your source temperature that ranges from 200 to 280 degrees Celsius depending on your analyte volatility. If it is too low, it will cause incomplete vaporization, and if it is too high, it would cause thermal degradation. So transfer line temperature, it typically ranges from 250 to 300 degrees Celsius. The importance of transfer line is that it transfers your analyte from column to your mass analyzer. So you have to keep all your analyte in gas phase. So that is why it ranges to 250 to 300 degrees Celsius. It is critical for preventing condensation and carryover. So let's talk about setting up your multi-reaction monitoring, that is MRM. This is the gold standard for GCMS quantitation. Let me walk you through the complete optimization process. So the first step is identifying your precursor ion. So what you have to do is prepare your 1 ppm of your standard and you need to run full scan mode to identify your molecular ion or whatever is your most abundant ion. For electron ionization, you often see molecular ion that is M plus and M minus H plus or other characteristic fragments. So you need to select whatever is your most stable and most abundant ion. You need to avoid low mass ions It may be coming from your background interferences. So after you do your full scan, you go to product ion scanning. Now in Q1, you allow only your precursor ion to pass, and you have to set Q3 to a scan mode, and you need to scan all the product ions. This will show all possible fragments from your precursor. So before moving to product ion scanning, let's understand the fragmentation patterns here. Electron ionization creates characteristic fragmentation. It breaks your weak bond that is adjacent to heteroatoms. Rearrangement can occur. Larger fragment is equal to more structural specificity, while smaller fragment is equal to more intense but less specific. So this is how your fragmentation usually happens. So let's look at the rules for selecting your product ions. So for quantifier ions, you have to select the most abundant for best sensitivity. And in qualifier ions, you have to select one or two additional ions for confirmation. And product ions should be greater than 50 mass to charge ratio. And what you shouldn't select, very low masses, that is below mass to charge ratio of 50. It causes too much background noises. It can account from water, ammonia or carbon dioxide loss. Now coming to your collision energy optimization. This is perhaps the most important and most misunderstood parameter in MSMS. So let's understand what is collision energy. Collision energy is the kinetic energy imparted to ions as they accelerated into the collision cell. It determines how much internal energy the ion gains and therefore how it fragments. There is collision energy paradox, that is, some people they think that if too low collision energy is given, there is no fragmentation. You will just see your precursor ion passing through. And if you give high collision energy, there will be over fragmentation. Ion breaks into small non-specific fragments, and an optimal depends on molecular structure, size and bond strength. Now, why collision energy optimization is complex is that recent research shows that collision energy response curves are not simple bell curves. They can show single maximum, simple, easy to optimize, broad plateau, that is wide working range, and third one is double peaks, that is it can consist of two optimal energies. The double peak phenomenon occurs because of B-type and Y-type fragments. They have different energy dependencies. So this is especially important for peptides but also applies to many organic molecules. Now let's come to your collision energy optimizing strategy. In traditionally, we used to infuse pure standard continuously, and we used to give varying collision energy, that is from 5 to 50 electrovolts in 5 electrovolt increments, and we used to monitor product ion intensity. So whichever collision energy used to give maximum signal, we used to use that collision energy. Now let's come to your advanced method of collision energy breakdown curves. Now this approach is more comprehensive. In this, you have to create method with multiple MRM transition. So you're going to keep same precursor, but product ion pair would be repeated, and each repetition uses different collision energy. Example 5, 10, 15, 20 and so on till 50 electron volts. And this all is done in single injection. So at last you get a graph, plot intensity versus collision energy for each transition. Now the advantage of this advanced method is that it visualizes entire collision energy response range, and it automatically identifies plateaus versus sharp peaks. And you can also test it in actual metrics and not just solvent. And it would also reveal if there is any matrix effect, and it would optimize the collision energy. So let's understand collision energy optimization by compound class. Now different compound types requires different approaches. That is, for small molecules below 200 mass to charge ratio, you can provide 10 to 25 electron volt of collision energy because it fragments easily. And for medium molecules from 200 to 400 mass to charge ratio, you can give 15 to 35 electron volt. And for large molecules, that is more than 400 mass to charge ratio, you can give between 25 to 50 electrovolts. Now let's talk about dwell time optimization. So what is dwell time? It is how long the MS monitors each MRM transition. So you need 10 to 15 minimum data points across your chromatographic peak. So cycle time equals number of transition into dwell time plus your interscan delay. Thus, peak sampling rate is equal to 1 divided your cycle time. Now let's talk about dwell time optimization strategy. So typically start with 25 to 50 milliseconds dwell time, and you need to adjust it depending on your peak width and number of transition. You can always go with scheduled MRM to reduce concurrent transition. Always remember, shorter dwell time is equal to more compound but less sensitivity. Longer dwell time will give you fewer compounds but more sensitivity. So let's talk about scheduled and dynamic MRM. This is a modern approach which uses retention time windows. It will monitor each compound only during its elution window. What is the uses of dynamic MRM? Is that it reduces concurrent transition, it allows longer dwell time, and can monitor hundreds of compounds with excellent sensitivity. Alright, let's recap the essential elements of GCMS method development. First is thorough planning. Know your objective, sensitivity requirement and metrics. Then GC separation, where you're going to select your column and you're going to do temperature programming. Last one is your MS optimization, where you're going to tune your analyte, you're going to optimize your precursor, then you're going to give collision energy to the precursor and you're going to select your product ion, then you're going to schedule your MRM, and then last one is dwell time balancing. The key to success is understanding the fundamental principle we have covered today, especially the MS optimization. Don't just use vendor default. Take time to truly optimize your collision energies and transition for your specific application. If you found this video helpful, please hit that like button and subscribe for more analytical chemistry content. Do drop a comment if you have questions regarding this video. Thanks for watching.